Okay. Oh, let me move this one. Okay, and so today we're going to cover data preprocessing, which is the first step in the KDD pipeline. And if you don't remember, we'll cover that in a second. Do a quick review. And so in terms of data preprocessing, it's including and doing cleaning. Ooh. Is there? Okay. Oh, what is this? Apologies. Okay. Okay, and let's just try this one. And so it's including cleaning. Oops, sorry. And includes cleaning and data integration. That means, so cleaning means, so for example, there's some problem with the data, for example, missing values or errors in the value. And then data integration, that means you might need data from multiple tables or files. So not just a single file, you need to integrate them. So there might be some overlap of the information saved in these different tables or files. And then data transformation, you need to change the format of the data. And it might not be in the format that can be used for the algorithms you want to use later on. So you need to change the format of the data. And finally, data reduction. And so sometimes the data is just too big, and then you can't really say it's too big for your machine to handle, and you might not need that much data anyway. So for example, when you first starting the analysis, you might not want to work on the entire data set. You want to select a subset. And so that's the data reduction. Oops. I don't know what happened. Okay, and as I mentioned, so last week we talked about the KDD model. And so that was KDD stands for knowledge discovery in database, and which is more from the database community. But the process is still valid or applicable to visual data analysis or visual analytics. And so you have the data, and the focusing is actually the part where we pick what you want to work on, and which we'll not cover because this is mostly an application dependent. And so we're going to cover preprocessing today, and that including some of the transformation. And we also will do later have lecture on data mining. I don't think we have time to cover evaluation. But this is the overall the KDD process, and we're going to be focusing on the preprocessing today. Okay, and then so sometimes it might be preferable to view the original raw data, and it's usually a good idea to make it at least an option. If people want to see the original data, they can. And so, yeah, examples including medical images, but even any data as you collect it, and it will be good at least to have the option to view the original data. Okay, and then so if you want to visualize the data, and you might need to do some pre-processing, so you probably would have experience of this already by doing, say, the coursework for the first and second coursework, and the data you were given might not fit into, say, Tableau or Altair nicely, then you have to do some pre-processing. And in terms, you either change the format of the data, and sometimes there's some problem in the data, you have to handle it first before it can be displayed. Okay, again, and so there's 4 different types of data preprocessing. And we said this first one is data cleansing. So this including spewing the missing values and smooth noisy data. So some data might be missing, smooth noisy data. So some of the measurement might not be correct. And you can obviously see it does not follow the certain trend. And it could be accurate in the sense that something abnormal happened when the data was captured, but it also could be there's some errors or just basically the sensor or the measurement itself is not very reliable, so it recording errors. And identify or remove outliers, and so it's usually useful to identify the outliers, and then depends how do you want to do afterwards. And you could remove them, or you could just say not considering them in the analysis. Sometimes these actually outliers are the things that you are interested in, so you want to actually focus on them. The example would be, for example, if you analyzing network security data, you want to identify cyber attacks to your networks. Usually these attacks actually are the outliers. So there's normal network traffic, and those are things you can actually ignore. The part you actually want to interested in is actually the outliers, and that will be what you're going to be focusing on. And resolving inconsistencies. Okay, and so that's data cleansing. And the second part is the data integration. As I said, and it's about integrating data from different databases and files or data cubes. Data cubes is just a term to describe a multi-dimensional data. So if you think of, say, you can have 2D data, which has 2 keys, and you can have data cubes, so it has multiple keys or dimensions. And data cubes, it looks still just like a spreadsheet, and it's no different. And sometimes the data comes actually in files, CSV, or even worse, some free text files, and you have to handle this. And so for integration, usually what you will need something like a common key to be able to integrate. And so this is most obvious. You'll be familiar with probably in database. For example, you have 2 tables, and to be able to join the information for 2 different tables, you have to have some columns which you can actually match the records from one table to the other. Otherwise, you can't really integrate. You can just say merge them together. Okay, and so in terms of data transformation, and that includes normalization and aggregation. So normalization, for example, the most common one is to convert all the values to the range between 0 and 1, because that works better. Also makes it consistent across different, say, data attributes. Okay, and finally, data reduction, reduce the number of records or attributes. So we talked about, say, if you have a very large data set, you maybe have millions of records or rows in it, and you might don't want to start with everything at the very beginning, at least. And this is also the same concept applies to the attributes, which are the columns in your tables. And maybe you have a very complex data set with hundreds or even thousands of columns. And maybe you want to say for your visual analysis, it usually will be quite difficult to at least start with, say, thousands different attributes. You might want to focus on certain of them. Okay, I'm going to start with the first part, which is the data cleansing. Okay, and so in the real world, no data is perfect, so you can always have errors. And so the examples we have been using so far from the machine learning data repository, I think it's called. There are many data sets there, and those are ones has already been cleaned. And so someone collected the data from the real world, like the car data set or the sepal and the pedal-less data. Those real world data has already been pre-processed in terms of, say, filling out any missing values and collect errors. And actually, if you're going to work in a company or work on a real project, and the data you have to start with is most likely to have many different types of issues. Okay, so one of the common data issue is missing values. So I guess, and the concept itself is straightforward. There's some attributes missing. For example, you don't have the price for a product, you don't have the names or the ID numbers, etc., etc. And it could be, say, just people forgot to enter them, or maybe the information just does not exist in your data collection. Or there's some errors, for example, from the measurement or sensor, so it didn't get the correct value. Okay, you could have empty values. Okay, and this is examples explaining. So the context will be this was the marketing research company. And so these are usually the companies, and they do research on behalf of other companies. And then they will get people to say usually and recruit some people and get them to do something. For example, in this case, maybe test a different food or drugs or even TV shows, anything. And then they ask people to fill out a questionnaire usually afterwards and see how well what do people think of this new product. Okay, and in this case, and the company needs to test 5 different products for ease of use and effectiveness. And so there are 5 things they need to test, 5 products, and they want to test for 2 things, ease of use and effectiveness. So ease of use, and these are 2 different things. So an ease of use is how easy to use it. And for example, a very intuitive product, so people don't have to read menus, they can use it straight away. And say something very difficult, you might have to read 10 pages of menus before even you know where to start. And then effectiveness means, and whether the product achieves the things they're supposed to do. A product can be very easy to use, but it doesn't really do what it's supposed to do, because there are 2 different things. Okay, so this will be the data they collected. And so I assume this stands for observations. This is the ID, and these are the 5 products they need to test. Okay, and usually most of them, they would have some values, but they would have these anomalies or the issues, say X indicator, tester absent. So we have an X here. So when, say, the participant 3, when he or she is supposed to test the 3rd product, which is food product 3, and he or she just not available, he's sick or something, so he didn't do the test. And so there's no. And then I indicates test was incomplete. Okay, and so for example here, and for the first person, he's supposed to test when the first participant to testing the first coffee product, and the product was not complete. Sorry, the test was not complete. And I don't know, could be anything happened. For example, there's some problems and with the supplier of the product. So when the person is supposed to say test the coffee, it's just not available, or it wasn't even cooked or brewed properly. So the person was not be able to test it or provide. So that is supposed to do, say, 5 steps, and only 3 steps are done. So that was not complete. Okay. Okay, and so there are many different ways to handling missing or empty values. And you can ignore the record. So basically, don't include those ones with missing values in your analysis. And this is okay if you have lots of data, but if you only have a few, and if you ignore all the records with missing values or empty values, then you might end up with very few to work with. Okay, and if you look at this one, and you only has 5 records, and 2 of them actually have issues. If you ignore those, and that means you only have 3 records to work with, that means you're kind of missing 40% of the data. You can't use them. So that can be an issue. And if you have 1,000 records and only 2 of them has missing values or issues, and so if you ignore those, you still have 109, 198 to work with. So that should not be, that would be much less an issue. Okay, and the other one is to fill in the missing value manually. That's the part, it's a bit tricky. Okay, and so you can use a default value to fill the missing part, say just unknown. So if you fill the missing value or empty value as unknown, it doesn't really changes anything. You still don't know what the value is. Actually, doesn't matter what you do. If you want to fill in the data manually, you still would not be able to know what the value is. And you can put in just unknown, in which case it doesn't really change anything. You don't still don't have a value. Okay, and you can use the attribute min to fill in the missing value. Okay, so in this case, okay, so for this one, it's not complete, so we don't have the value. You could replace the I with the average of these other values. You say, okay, that might be the likely values for this one. Similarly, for the X, you can average 65, 55, 43, 39, give the average value. So that's an kind of it's a guess, and it's probably better than a random number. But still, and we really don't know how good that it is. But maybe better than not having it, and especially if we have to include that in the test or in the analysis. Okay, and the next one will be use the most probable value to fill in the missing one. Okay, and so this one is similar to this. So you want to somehow estimate or guess what the missing value is. And is to say sometimes you might be use a more advanced method, or depends on the situation compared to just using average. Okay, and so we set something like this. So these are the ones we're going to cover later on, and not necessarily in data cleaning. But you probably would have, say, recognize some of this, for example, regression or decision trees are related to machine learning. And so the general idea would be, okay, so I don't know what the value of this is, but I do know what the other values are from this participant. What you can potentially do, instead of just using the average of the other values, you can say, okay, if I look at the other 4 values, which person are similar to this person? They have a similar, but say, taste compared to this person. And then maybe I can use those people's coffee 1 value to estimate what this would be. So in theory, this will be more accurate than, say, just averaging everybody. So if you first find out the people has similar taste to this person, and maybe average theirs, or in using a weighted way. So you can do it more complex ways, and hopefully, to reduce the errors between, or the differences between the guessed value, estimated value, and the real value, which itself is not possible to measure. Okay, and so this is the missing or the empty values. And next one is noisy data. And so this is just could be random errors. The machine you use to measure the thing just somehow stopped working. It's not very reliable. And also, and sometimes it's the variance and in the measured attributes. Okay, so all the measurements you do would have some variance. And it just depends on how accurate or how precise the tools you use to measure. And for example, if you have to estimate the height of a person, and the variance might be quite big. So one person may think, okay, this person is 1.8, the other person may think it's 1.75, another one think maybe 1.85 meters. So these are the difference and is the variance. And if you use a ruler or a height measure, the variance will be much smaller, and the person might be 1.8. The actual height might be 1.82 meters, and the person when you measure it, every time you might have a slightly different value, for example, but the difference or the variance might be much smaller than say just estimate by a person. So maybe the variance might be within 1 centimeters. Okay, but it always be, so they will not be exactly the same if you do multiple measurements. Okay, and so this could happen, and because the instrument doesn't work properly, for example, you use a machine to measure height, somehow there's some problem with the machine, so the height wasn't measured properly. And could be data entry problems. Let's say to manually write down the height, you just somehow write the wrong number down. I mean, the chance of this happening is quite small, but it could happen. The transmission problems, when you transfer the data from the measurement to a record, something might happen, so data is not recorded correctly. And technical limitations. I don't know, for example, you have to measure something very, very high. Let's say you have to measure something very high speed or high temperature, like 10,000 degrees. And there's just nothing you can actually, there's no thermometer can withstand 10,000 degrees. And just not possible to have a very accurate reading. And finally, inconsistent in naming conventions. And just because the way to record the information is different, that might cause errors. Okay, and in terms of handling noisy data, okay, one way to do this, you can do binning, and you sort data and partition them into equal depth bins. Okay, and I'm going to explain this a little bit later on what these means. Okay, and then once you've done that, you can smooth by the bin the means, median, or boundaries. So basically, binning kind of is like grouping the data or put data into different buckets. That's what the term binning comes from. So all the data within the same group or bucket is usually, or the same bin, is usually the data which are similar. And then there's always the option of how do you create these bins. For example, you can make the bin, each bin contains the same number of data points, and then the size of the bins might be different, because for the range which has lots of values, the bin will be quite small, and for the range which has little values, you have to a very large bin to include lots of things. And equal depth bins means you can also make the bins have the same size always, but then the number of data points within each bin will be different. Okay, and you can do regression. Essentially, you try to say, assuming there's the data distribution following certain kind of a straight line or curve, in some sort, and then you can say what are the noises based on that assumption. And you can do clustering. Again, this is similar to binning, but usually the clustering is in multiple dimensions. And usually, each dimension is not necessarily, say, the X, Y, or Z. It could be a combination of X, Y, and Z. And this allows you to say which one are the outliers, similar to regression. Okay, and then finally, you can always include the human in the process. And based on human background or the knowledge about the domain, they might be able to detect suspicious values. Okay, and so a little bit back about the binning. So the equal width bin or the equidepth bin, sorry, just equal width bin. And so you'll divide the entire data range into n intervals of equal size. Okay, and so this is what this looks like. Let's say the entire data set you have, okay, let's say this is your entire data set. These are the numbers you have from some measurements. And the equal width bin is like this. So each of these blocks is a bin, and the width is always the same. In this case, is always 10. And then as a result, the number of measurements within each bin will be different. So this has 3, 4, and 5. So this is equal. And the other one is called equal depth bin. So you can imagine this will be the width of the bin, and this will be the depth of the bin. So equal depth is you still have the same number of bins like this one, but they all have the same number of measurements inside. So you have this 1, 2, and 3. All of them has 4 numbers of whole measurements inside, but then you can see the width of the bin is different just because the distribution, the data, because it's more skewed towards this hand side. So you need a wider bin at the beginning, including 4 numbers, 4 and 4. So equal width and equal depth. Okay, and so the data smoothing. So smoothing usually just means reduce the variance among the data. Okay, this is essentially kind of actually reduce the information you get from the data, but sometimes it's needed if you need to reduce the amount of the data you have to handle. So in this case, for example, once you have the bins, you can use 1 or 2 numbers to represent each bin instead of using all the numbers or measurements within a bin. Okay, and let's say this is your data and this is your bin. In this case, it will have the equal this depth bin. So that means each bin contains the same number of data or measurements, which is 4. Okay, and you can do smoothing. This example is smoothing by the mean. And so you basically replace all the measurements in the bin using the mean of all the measurements. In this case will be 5. Okay, and as I said, this lose some information, but sometimes it's useful if you need to reduce the data. And then you can, for the second one, you can just do the average of these 4 numbers, and then you replace all the numbers with that. Or really, you just say that the bin number, just essentially just associate the bin with one measurement, which is 23, and same for the third one, which is 29. Okay, and there's many different ways to do this. You can use mean, you can use median, and this is another one, is to replace the value by the closest boundary values. Okay, so if we look at this one, the 2 boundary values are 4 and 15. And then for everything in between, depends on which end it's closest to, and it will be replaced with that value. So the 8 is closer to 4 than to 15, so that will be replaced by 4. And then 9 is closer to 15 compared to 4, so that will be replaced with 15. That's why you get this. Okay, and essentially this reduce and each bin into just 2 measurements, which are the 2 extremes, the minimum and the maximum of that bin. Sometimes it might be useful, but again, you lose some information, so you don't really know what those actual measurements are anymore. Okay, and so this is the way of using regression for data smoothing, and it's also a similar concept, and you can apply the same regression for missing value as well. Okay, so in the smoothing, in the sense, well, okay, and you always have this assumption, say, and the data follows certain distribution. That might not be the case. Or also, for example, in this case, the assumption is the data follow a linear distribution. So there's a linear relationship between the x and y. Okay, and that might not be true. And it might be a cubic or quadratic or some other nonlinear relationships. So that's a decision you have to make, or assumption you have to make. Okay, and once you assume there's a linear relationship between x and y, and you can replace y1 with y1 prime, which is this one here, because if we assume the data should all follow this trend, then this is likely to be an outlier, and then we assume that's probably because some errors in the measurement. So we can replace this one, y1 with y1 prime. Okay, and it's similar thing. If it's missing value, for example, y1 is missing, you don't know what it is, and then you can do a regression, and you then use that to estimate what y1 might be like. And yeah, and so this, and again, the regression, it can be linear, can be quadratic, or other type of distributions. And sometimes this should be used, depends on, say, you need to use domain knowledges to understand based on what x and y is and what their relationship usually is in reality. Okay, and it always depends. Say, the assumption that data actually follows certain distributions, that might not be the case. Okay, and next I'm going to talk about the data integration. So combine data from multiple sources into a single data collection or single, and not necessarily databases, because the term database itself sometimes can be too much associated with the software. But really, we are talking about in a more conceptual level, just a collection of data. And if you have to see it, it might be something like a spreadsheet or a table in my SQL database. But we are talking at the more abstract level, just a collection of data. Okay, and then so this is including integrating metadata from different sources. And then you have this attribute identification problems. Okay, and so okay, so one example here in terms of schema integration. So if you know schema and in the database, so the schema defines, okay, how many columns a table has, what are the types of each column, but also defines what are each columns, what is the information that each column stores. So maybe the first column is student ID, and the second column is student name, the third column is, I don't know, student gender, and so on and so forth. Okay, and then you might have two systems, they both store student information, but say in the one table, you have three columns. So for student name, so you have the middle name, sorry, you have the first name, middle name, and last name. And in the other table, you only have one column for student name, just name, and you put everything inside there. And then you have to be able to match the three columns from the first table to the single column in the second table. Yeah. And so this is still conceptually not too difficult to do, but sometimes the way the data is organized makes it very much difficult to integrate. Okay, And also sometimes they just simply have different names. So for example, you might have gender, called gender in one column and sex in the other table. Again, so these are the relatively easy ones. You can just say, okay, gender in table 1 is the same as sex in table 2. Okay, and then so this is the schema integration. So essentially mapping the columns of different tables. And then you have the instance integration. So just think of instance as the rows in tables, say different products or different each and every single student. And you need to find out, okay, is the John Smith in table 1 the same John Smith in table 2? So they could be the same person, but also could be 2 different people just with the same name. Okay, and again, it's not always possible to do this precisely. And the easiest thing, for example, you have a unique ID. For example, every student have a different ID, then you can just matching the ID, then you know which one is which. But for example, and in the real world, for example, for all the people in UK, not every person has a unique ID. And you have to use, say, a name or maybe the date of birth and address, try to match. And even those you can never guarantee. So the 2 people can have the same name and same date of birth, but they still are 2 different people. Okay, and so first thing, so actually before you can do say either the schema or the instance, basically columns or row integration, you have to find out the relevant tables from different data sources. Maybe you have 2 databases, each has many tables. The first one has 30, the second one have 200. You have to first find out which table from the first database matches to which table from the second database. That itself is not an easy work, or not always possible. And then you find the matching attributes. So this is the schema or the column matching, and then you find the corresponding records. So this is here, the instance, the row, which row in the first collection is the same mapped to which row in the second collection. Yeah. Okay, and once you're done, you can merge corresponding tables. And so that means merging the attributes, and maybe you can matching the student from the first table to the students in the second table, and then you can merge. For example, the first table has the student, I don't know, say contact information. So it has their phone number, their email address, and the second table have the students' results, the academic results. So which module they have done, what their mark is for the grade is for each module. And then you can have a merged table, which has both the student contact and the academic results. And also you can remove duplicate records. And for example, so the duplicate record only works if you have, how do I say? So if you have the same person, the record appeared multiple times in the same table, and that person, you only need one. You don't have to do all the other multiple copies. Okay, and next part is about the normalization. I know. Okay, where's my mouse? And what it does is to make makes different records comparable, and usually, for example, convert all the values to the range between 0 and 1. That's the most common one. Okay, another is to discretization. And so, for example, you have some measurements. I don't know, maybe the height of a person, and it's a continuous value. So it could be any, so basically there's an infinite number of possible values, because sometimes this is some of the method you want to use cannot handle that. Then you have to discretization. Okay. And then you might want to, sometimes you have to create new attributes. And for example, in your product information table, you have the, I don't know, the sales for a product and also the cost of the product. And you might create a new attribute, a column called a profit of the product, by taking the sales and then minus the cost, and then the difference will be the profit. Okay, and normalization is particularly useful, and if you have many different dimensions, and sometimes the high dimensional, large number of dimensions just translate to many number of columns in your table. Okay, and in this case, and if you don't normalize, essentially that means makes the values of all the dimensions within the same range, between 0, 1 or 0 and 100, anything. And then the distance measures will overweight those that has a larger values. Okay, and let's have a look at example. So this is a very simple example. The actual one might be much more complex. So this is a table which records the age and height of each person. So this is the actual age of the person. So for example, Jim is just born, and this is the height of the person. Okay. Okay. And so if you want to say calculate and how similar or different two persons are, and based on their age and height, and you can calculate the distance, and almost like using Euclidean distance, if that makes sense. So you can treat age as X and height as Y. And you can say, okay, what is the difference between Jim and Andy? And you can calculate just using the Euclidean distance, using age and X and height and Y. Okay, back to normalization. And because, and this one is measured in centimeters, and then by default, this will have a large contribution when calculating the distance. Yeah, compared to this one, because say the age has a smaller possible value. So age is, let's say, usually between 0 and 100, and maybe slightly more than 100, but the height would start from 30, maybe to 200 something, 220 or something. Okay, so this would have more impact. So that might not be desirable, and because when you want to see the difference between the person, and you possibly want to have, say, the age or height contribute equally to the distance, or sometimes you might want to have your own weightings. You want to say age has more impact than the height, but again, these will be probably different from the actual values of the way they are. Now, another way to think about this, for example, if you measure height instead of in the centimeters, you measure height in meters, and then all the values you're going to get will be, say, 0.3, 2.05, and 0.8. And these values suddenly becomes very small in the overall contribution to the distance between the people, because in comparison to the age, and its value will be between 0 and 100, this will be, say, 0.3 and 2.5 maximum, for example. Okay, and then, so the normalization, And I'm gonna just spare you with all the mathematics, just explain the main concept. And so this will be in the range of your data. So you find the minimum and the maximum values of your data, and you somehow transform that into the range between 0 and 1. So this is like a common approach. And you can pick different values. You can pick, I don't know, 0 to 10, 0 to 100. You can pick to -1 to 23 or something that you can decide. But usually the thing is, and you want to do this, you have the same range for all the different attributes. And so, for example, you converted the age between 0 and 1, you can convert height also between 0 and 1. And again, oh, sorry. And then there are many different ways and how to do this conversion. So obviously, and probably the easiest way is to just to do linear mapping. So let's just say the maximum value is 0 and the largest value is 1. Let's say if it is the age, the minimum age is 0 and the maximum age is 100. So if someone is 50 years old, it will map to a value of 0.5. If it's 20 years old, it will be 0.2. And that's the linear conversion. Okay. And so here shows the example. We have 3 numbers, minimum and maximum. And so this will be 0 and this will be 1. And this will be somewhere in between. In this case, that's the formula. And that gives you the value of 0.2. Okay. As I mentioned, linear is the easiest one or the most simple one. It does not always work properly. And sometimes, and you want to do the other type of mapping, so you can do square root mapping. And still, and the minimum is always still 0. The maximum will always be 1. It's just the values in between, they'll get slightly different values, depends on the mapping itself. So in this case, going to do square root. And so you can see the formula here. Compared to this one, all these variables is the same, except it has now have a square root on top. That's the only difference. And in this case, now and 16 is 0.33 instead of 0.2. Okay. Again, there's no right or wrong mapping, and you need to pick, say, either linear or square root or some other ways, depends on the actual application, which one actually matches the real world better. Okay, and also finally, you have logarithmic mapping. And the formula, again, it's just the operations before each of these variables are different. It's still, these variables are still the same, but instead of square, now it will become log. And the result would be, again, the minimum value is always 0, the maximum is always 1, and then this one now becomes 0.5. Okay, and I just want to repeat again, there's no correct way to say linear is always better than square root. There's no such thing. And you need to you choose the right mapping and depends on your application. But usually it is true, say, if you have a multi-dimensional data and you want to do some analysis which involves more than one dimensions or attributes, you probably should normalize them first. So it doesn't end up by having the attributes have the largest numbers to influence and most the results. Okay, next one is for discretization. Okay, so the opposite of discrete values is the continuous values. So these are the real numbers. So you can have 1.2. So for example, the value of pi is a continuous value, Whereas say a natural number like 1, 2, 3, 4, these are discrete numbers. Okay, and some of the data mining algorithm only accepts categorical attributes. And then sometimes they can only accept discrete stuff. So the categorical is a bit different again. So categorical attributes, it doesn't have any particular order. Okay, and say in this case, if I want to have a number which it still has, and just so long as it's not continuous, and you can using binning, which we talked about before, and you can bin the numbers or the collections of numbers first, and use one number or two to represent each bin. So that gives you only a few numbers rather than say all possible numbers. And you can also do class analysis, which we'll cover. Can't remember if it's this or next lecture, or entropy-based discretization, which we will not cover. Okay, and we're going to talk more about those later. But for now, we just go straight to the next part, and which is about data reduction. Yeah. Okay, and the reason why we want to do data reduction. So first one is to improve the efficiency, and depends on the algorithms, but usually an analysis algorithm will take longer time if you have more data, more number of records in your table, for example. And ideally, if you can achieve the same results or accuracy with less number of records, then that means you can get the results faster. And the other one potentially is to improve quality. And say, if you remove the noisy data or noisy attributes, and it might improve the overall result. And for example, we talked about before, you might have missing data or noisy data or errors in your data, in your table, and the remove those can potentially improve the overall quality of the results. But this only works if you know actually what is an error, or what is, for example, you want to remove noisy data, but you have to know what is considered noise and what is not. Sometimes you might not know. And something might look like an outlier, but actually it might be real data. It's actually true. It's how the distribution is. Okay, anyway, and so in terms of the actual data reduction, you want to reduce the number of attributes, so number of columns, and or the number of records, so number of rows. So you can do either attributes, record, or records, or both. Okay, and so okay. You can to reduce dimensional data. Okay, so the project to reduce the number of columns or dimensions, you can do projection. And you can from the high dimensional data to low dimensional data. So this does not change the number of data records. If you have 2,000 rows in your table, you still have 2,000 rows, and just number of the columns reduced. And this, the reason we call this projection instead of just simply, so it's not just simply remove some columns. Instead, in most of the cases, those projection methods we talk about will just be combining some of the columns. Okay, so that's called projection. And for this side, so this side you reduce, or this direction, you reduce the number of rows, but you keep the number of the columns. So if you have 10 attributes, you still have 10 after clustering, but the number of the rows will be reduced. And so in a sense, so we already talked about the binning. So that can be treated as one form of clustering. So you can reduce the total number of rows to the number of bins you have. So you don't further differentiate within each bins, then the number of rows can reduce from 10,000 to say 3 bins. That's a lot of reduction. It might still be acceptable. So the results, the calculation analysis will be faster, but the cost will be, say, you lose lots of information. Okay, so this side or this direction to reduce the number of columns, you can just reduce the number of rows, and you can do samples. And samples just basically means you pick some rows to remove. Okay, and so you can say you might want to remove certain type of product and from your database and from your product database. Or you can do, okay, let's say maybe it's actually easy to start with the probabilistic samples. So that means you randomly remove data from your, so randomly remove rows from your tables to reduce the overall size. And in the hope, you still, so it does not affect the overall distribution of the data. And so the opposite of the probabilistic samples is the non-probabilistic samples. That means you're actually following certain rules to remove only certain type of rows that will affect overall data distribution. Depends on which one of these is what you want to achieve. Okay, and so the problem with the random sampling is maybe they were going to overlook small but important groups. And so if you only say randomly remove, well, let's say randomly keep rows from your table, and then because the small groups, they are less likely to be selected because they have small number, so it might not include it in the result at all, then that might be missing from your analysis later. Okay, and so the way to do this is you can do stratified sampling or classed sampling, and which follows similar ideas. So first you identify the different stratum. It basically means a group or like a bin, or cluster, which means within each cluster, the data are similar. And then for each stratum or cluster, you pick some samples from it. Then you know at least, say, each cluster or group is included in the sample. To avoid these problems, you might missing some small groups. Okay, and so this is the simple random sampling. So this, let's say this is your entire data set, and these are the points, the random sampled points. You just get data from these points, and you can use that information to describe the area. And the certain information, for example, I don't know, maybe this is a peak or a valley somewhere, but because that's not included in the sampling, so that will be not represented in the result. Okay, and this is stratified random sampling. And first, you group your data set into non-overlapping subsets. So these are called strata. And then sampling from the strata is then simply random. And so let's say this is your entire, okay, this is your entire data set with all the clients you have. And then you can group these clients into stratas by ethnicity. So these are Caucasians, these are African Americans, and Hispanic Americans. Okay, and there's many other different ways, dimensions. You can say create strata, or the groups based on age, on the gender, many other attributes. Okay, and usually you can only do one, you can't do multiple at the same time. And what you could do, and then, okay, let's not go to the too complex example. And then within each group, you random pick some samples. Okay, now we go to the other side. If you remember, I'm going to reduce the number of columns. So what we talked about before is to reduce the number of rows, which is kind of this direction. Now we're going to talk about reduce the number of columns, which is this direction. And so you want to select a subset of all attributes. So you don't want to including all the attributes. This is this is relevant when you have too many and columns, you have hundreds or even thousands. Okay, and so this can be quite useful. It's for, say, classification. Okay. So if you have, I don't know, so if you want to group your, say, what is classification? And maybe you want to do a classification on all your products to put them into, I don't know, and what would be to have good potential to grow or have little potential to grow, something like that. And then for the, obviously, the more features you include or more columns you include the classifier, and the slower it'll get to run. But also if you're including something which is not relevant as part of the classifier input, it might not help by making the performance worse. But let's just assume all the columns are useful, but still, if you have 2,000 attributes for each product, it's still too many for most classifiers, or going to be too slow to run. And so you want to select. And so one way to decide which attribute to include is through correlation analysis. Okay, so if you find, so I assume all of you would understand what correlation is. So basically, if the values in one attribute increase, the other also increase. And if that decrease, the other also decrease. That means there's a strong correlation. So that's a strong positive correlation. And you can also have negative ones. So they are move opposite and almost all the time. Okay, and so if there's strong correlation between two variables, that means you only really need to include the one because you can predict the movement of the other using the one you know. And all the other words, the second attribute doesn't really bring any new information. Okay, and so this is the Pearson's correlation. I'm not gonna go through the formula now, but really it gives you the value between -1 and +1. So +1 is 100% correlated positively, and -1 is negatively correlated 100%, and 0 is not correlated at all. So the actual value is usually between positive -1 and 1. Okay, and then the other way, this is like the more advanced way to do this and more related to, say, data mining or machine learning, is an dimensionality reduction. Okay, here it does not just simply remove columns. So previously, when we talk about, say, these correlation analysis, if you find, say, two columns are highly correlated, then you can remove any one of them, only keep the other one. Okay, here we don't just simply remove columns. We try to create new dimensions, which is sometimes, for example, a linear combination of existing ones to represent data instead of using the existing ones. And so examples including PCA and MDS. And PCA stands for Principal Component Analysis, and MDS stands for multidimensional scaling. These are quite a classical method for dimensionality reduction. Okay, so PCA, Principal Component Analysis. Okay. So the PCA is based on two assumptions. That's very important. If these are not met, then the result will not be very, the result of PCA will not be very representative of the original data. And so the first one is, and you can approximate or represent the original data using a linear subspace, linear relationship between the dimensions. And it's tried to preserve of the variance. So that means it tried to say, once you reduce the number of columns, what it tried to maintain or preserve is the distance between the points. And so if the distance between 2 points is far away in the high dimensional space, it tried to keep the distance still far away in the reduced space or the reduced number of dimensions. Okay, it does not consider anything else, only the distance between points. It does not consider, for example, I don't know, the length or the clustering or the grouping. Let us say the grouping or clustering is actually related to distance. Okay. So this is like a very simple example of the PCA. Let's say this original data is only 2 dimensions. So you have the X and Y dimension. So the only way to reduce it is just to maybe reduce to a single dimension. Okay. And one option will be you can just reduce to either X1 or X2. And for the PCA, it will pick a new axis, which is called Y1. And it's not X1 or X2. It's a linear combination of X1 and X2. And the reason it picks or to pick Y1 is because in this dimension, you have the most spread of the data. Yeah, so that's the reason they picked Y1 instead of an X1 or X2. And you can imagine, you can pick, if you have lots of dimensions, and you can pick Y1 first, and then Y2, which will be orthogonal to Y1, and then Y3 and 4 and 5, and so on and so forth. Okay. Can I see the time? Couldn't see the time. What happened? Give me a minute. Just try to get this one to work. Where's my mouse? Yep. Okay. Yeah. Ooh. Okay. Yeah, so this part getting a little bit, say, mathematical, but hopefully it will be useful. And at least you can easily understand and the variance. Okay, so that means how much variation in the data it captures, and you want that to be as big as possible. And so usually in the principal component analysis, and this is your component basically means axis, and that's your principal or the first component. So that needs to be the one which captures the most variance. That means along that axis, there's the widest range in the data. This is what you get here. So that component captures 36.6% of the overall variance, and then you add a second one that capture another 20% something, and then the cumulative ones will becomes this much. And then as it goes on, this is the 10th dimension already. It only covers really very little additional variance. And then the total variance will be 94.77. So that almost covered the entire variance in the original data set in terms of the distance between the points. So maybe the original data set is have 200 dimensions, and then you can use these 10, which covers the most variance already. Okay. And there's also this thing called eigenvalue. I don't have any good examples here. And correlation. Okay. So there's also this value we had here called eigenvector. If you studied, say, linear algebra, you will know eigenvector, but in the context of the matrix. And this is kind of similar meanings. So, and it's trying to measure the correlations between the variables and principal axes. So that is your principal axis. And essentially what it measures and is for each variable, a variable will be an attribute or column in your collection, in your database or relational table. And how much does that contribute to a component? And the component here just means these axes. So that's the first component, second component, and so on and so forth. So basically, the higher the eigenvalue, the more an attribute contribute to that particular axis or component. Yeah. And I think you don't run into fully understand these, and for the, say, when you're doing data analysis, and in most of these softwares, the PCA will be already implemented. All you need to do is just to load data and press the PCA button, and then it will run and give you some of these and different components. Okay. And also will calculate eigenvector for you as well. But I think more importantly, just to understand the kind of understand what eigenvector indicates, that indicates and the contribution of a variable to a component. So the higher the value, the more particularly variable, which is a dimension in the original data, contributes to a component, which is an axis in the PCA. Okay, and that's it. I'm gonna stop there. So today we cover the data pre-processing, and that includes the cleansing, which is about, say, the missing data, empty values or errors, and data integration, about getting data from different sources, essentially matching either the schema, the columns, or the rows instances. And data transformation, we talk about how do you map different dimensions in between the range of 0 and 1. They have to do the linear or square root or logarithmic, different ways. And finally, we talk about data reduction, again, reducing either in terms of number of rows or number of columns. Number of rows, you can do just sampling, which is random pick something, or you can do some clustering first and then do sampling. And in terms of the reduction of the dimensions, attributes, and you can do either just pick something, but more complex ones in terms like the PCA, which is talked about. Okay, and that's it.